Okay, hello and welcome everyone. Today I'm going to talk to you about an effect that we and now others have shown time and time again, and that is that older adults form more non-target associations than younger adults, an effect that we've termed hyperbinding. And my recent work has started to examine the implications of this hyperbinding effect for older adults' memory for events experienced in everyday life. So as we move through the world, we sort of experience life as a continuous stream of events. But events are not stored in memory in this way, and rather they're divided up into a series of discrete units. So for instance, my day so far might be characterized by, eating breakfast with my family, followed by walking to school, and then finally sitting down to work on this talk. And research suggests that we experience these event boundaries, and this is work by Jeff Sachs and Gabe Radvansky and others. We experience event boundaries when we perceive sort of a change in space or time. You know, there's perceptual changes moving from, say, my living room to the outside world here. But also when we experience sort of internal shifts, such as a change in our goals. So for instance, after my kids are done eating breakfast, our goal might then change to getting dressed and getting ready to go to school. So whenever those things happen, people experience an event boundary. And what happens to our processing of the world at these event boundaries? Well, research has shown that event boundaries lead to a sort of working memory updating effect, or our event models are updated at these boundaries. So for instance, in a now classic study by Radvansky and Copeland, they had participants navigate through this virtual environment through a series of rooms. And within each room, there were two tables. At one table, they would pick up an object that was sitting on the table and put it into sort of virtual backpack. They couldn't see which object was in the virtual backpack at any given time. And they were supposed to move from that table to another table, put the object down and pick up another one and put it in the backpack. Once in a while, they would probe memory for what object was currently being held in this backpack. Now, critically, sometimes that probe could come while participants were in the same room, but other times it would happen after they had just walked through a door or experienced an event boundary. And what they found was that participants were slower to access and also less accurate in saying which object was currently in the backpack after they had passed through a boundary or walked through a door than if they were tested in the same room. So this suggests that these event boundaries serve to sort of update our working memory space and help us put previously attended information out of mind. But event boundaries don't only just affect, the contents of working memory, but they are also shown to have consequences for long-term memory. So event boundaries trigger brain mechanisms that seem to bind together the detail of a just experienced event, as indicated by increased hippocampal activity at event boundaries, and this is work by Aya Ben-Yaakov. And it also seems like those binding mechanisms might serve to sort of store the details of an event as a sort of tightly associated unit, with details better recalled when a cue is taken from within an event rather than one that just happens just before an event boundary. And this is work by Eziat and Devashi has shown this. So cued recall is better when taken from within an event than across an event boundary. And this raises the question of, what happens to these discrete event memories when working memory updating processes are impaired? So for instance, with advancing age. So now there's a long line of work suggesting that older adults have trouble inhibiting recently attended information in order to move on to another task. And I won't go into all of that work here. But, it sort of raises the issue, or it suggests that older adults might actually experience this sort of bleeding effect with the details from one moment sort of leading into the next if they are unable to put those details out of mind. And we have reason to believe that this failed suppression of recently attended information won't just negatively affect concurrent processing. So for instance, like Cindy Lustig has shown with recently attended information leading to interference in working memory, but it seems like older adults, in that they hold on to this recently attended information, it might have long-term consequences, in that older adults might be more likely to hyperbind, as I mentioned before, these recently attended information in with the currently attended information. So just to provide an overview of what I'm going to talk about today, first I'm going to provide a more thorough explanation of what I mean by hyperbinding. And then I'm going to show how hyperbinding can affect memory for successive word pairs within a standard paired associate learning task. So that's hyperbinding over time. And then I'm going to move on to how this sort of hyperbinding effect might extend to our encoding of naturalistic stimuli, such as movies. And finally discuss the theoretical and practical implications for older adults' memory in everyday life. So first of all, what is hyperbinding? Well, as I've already said, older adults have trouble inhibiting concurrent distraction and also putting previously attended information out of mind. And we have shown that this leads them to actually form more excess associations than younger adults, or to hyperbind. They bind all this irrelevant information together. And this effect really relies on two assumptions, or this theory relies on two assumptions. First of all is that co-attended information is automatically bound together. So by virtue of having two pieces of, or paying attention to two pieces of information, past work suggests that that information can become automatically bound together, likely by the hippocampus. And second of all is the view that automatic processes are relatively unaffected by age, and it's actually controlled top-down processes that are change most across the lifespan. So what evidence do we have for this hyperbinding effect? Well, first of all, in our first study on this, we showed that older adults bind co-occurring targets and distractors. So in this case, we had participants perform a one-back task on these pictures that were superimposed with distracting words. And we later tested to see if they transferred knowledge of those pairs of information they saw during the one-back task affected their memory performance on an intentional paired associate learning task. And what we saw was that when the pairings remained intact, it gave a boost to older adults' memory performance on that later task. But when we rearranged the pairs, it actually interfered with their ability to form associations, and they did worse for those pairs on that later task. We've also shown, using a visual statistical learning paradigm, that older adults actually learn these triplet sequences that are contained entirely within distracting information. Say they were told to ignore the red objects in this case. And we also have shown that this effect seems to depend on an implicit memory test. So, on the original study, when we asked participants to explicitly tell us what word was seen with the cabbage at study, they're unable to do so. And later we showed, if we alert them to the fact that some of these pairs they've seen before, it also disrupts this effect. So it really does seem to depend on implicit test conditions. And we aren't the only ones who have shown intact implicit associative memory with age. Around the same time as our original paper on hyperbinding, Kelly Giovanello showed that when associative memory is tested in a fully implicit manner, that older adults show no evidence of a binding deficit. So in that study, what they did was they showed participants pairs of objects, and they had to decide if those two objects could fit together inside a common desk drawer. They were supposed to respond as fast as they can. And then at test, they made the same decision again. Could these two objects fit together inside a common desk drawer? Importantly, on this test task, half of the pairs remained intact. That is, they saw the same pair at test, and half of them were rearranged. And what they found was that participants were faster to make this decision on the test task when the pair was intact versus rearranged, even though the individual items were equally familiar. and there were no age differences in this effect. So this suggests that older adults are able to learn this information and can show that to you, or they're able to learn these associations, and they can show that to you when it's tested implicitly in this case. So we recently adapted this paradigm to first of all see if we could replicate the effects of Do and Giovanello. And we also wanted to test for hyperbinding of targets and distractors in this new implicit memory task. So this is work that was led by Emily Davis, a grad student in my lab, and also Ethan Foy, who is an honors thesis student. And we had participants learn encode this information across 3 different types of blocks. First of all, we had a non-binding or a no-binding block. We call it no binding in that there's no information, there's no binding to be done, in that the letter string was a non-word. And participants were just supposed to look at the object, the pictured object, and decide whether that object could fit inside a comma's desk drawer on its own. We can contrast this with what I call a distraction block. And now the overlapping word is actually an object word, but participants are still being told to ignore the word and decide, could the pictured object alone fit inside a desk drawer? And then we have what we call the full attention block, where participants are told to pay attention to both the word and the pictured object and decide, could both objects fit together inside a common desk drawer? These encoding blocks were followed by a filled interval for about 10 minutes, and then participants were given the implicit associative memory task. So now they're making that same decision, could both objects fit together inside a common desk drawer? But importantly, there's 2 kinds of pairs at test. There's intact pairs, these are ones that they saw together during the encoding phase, and rearranged pairs. And pairs could be taken from any of the 3 blocks. We'll focus more on these 2 blocks. So if we're going to replicate the findings of Do and Giovanello, then we'd expect both older and younger adults to respond more quickly to intact pairs than rearranged pairs from the full attention block, when everybody is supposed to attend to both of the objects. Whereas from a hyperbinding perspective, we would expect that only older adults would show faster response times for intact than rearranged pairs from this distraction block. Whereas young adults should be good at ignoring those irrelevant words, and so they shouldn't learn these associations. So first of all, I'm showing you now the reaction times from the test phase. First of all, for the full attention condition, when they're supposed to pay attention to both the word and the object. And what we're seeing for older adults is faster responding for intact than rearranged pairs. Whereas, surprisingly, actually, for the young adults, we didn't find this effect of faster responding, or at least it wasn't significant for the intact versus rearranged. And then we replicated this again in a second experiment. I think what's going on, at least in this subset of young adults, is that they're responding very quickly on this task, and they might actually be at floor, and that we can't get them to go any faster for the intact pairs. They're responding faster than they did in the Giovanello study. Moving on to the pairs taken from the distraction block, we again see that older adults are responding faster to these intact than the rearranged pairs. In this case now for pairings that they shouldn't have learned in the first place, in that they should have ignored the distracting words. And again, young adults are showing no difference between the intact and the rearranged pairs. So this suggests that older adults bind co-occurring targets and distractors. And it shows that this hyperbinding effect extends to a novel implicit associative memory paradigm. And we've also shown again that associative memory seems to be preserved with age, at least when it's tested implicitly. So the studies I've discussed so far have shown that older adults form associations between co-occurring targets and distractors. But what about in a normal memory paradigm where there aren't distracting words hanging around? Is there any evidence for hyperbinding in this case? Well, so that's the question I'm going to address in the second part of my talk, is whether older adults form broader associations over time in a standard associative memory paradigm. So for instance, they bind across successive pairs within a paired associate learning task. So really, this requires us to first talk about this concept of deletion. So in addition to being able to ignore distracting information that's currently in the environment, we also need to be able to delete or inhibit recently attended information that's no longer relevant to the task at hand. You know, we need to put the past out of mind in order to focus on the present. And several cognitive tasks require the deletion of previously attended information. So for instance, on a working memory task, you might solve a series of equations and remember the words from that trial, recall those words, and then you move on to the next trial where you have to do the same thing again. In order to do well on that task, you really need to put that previous set of words out of mind in order to be able to recall the current set. And just a little plug for the recent special issue of Psych and Aging that I co-edited with Cindy Lustig and Lynn Hasher. That was all about inhibition. We discussed this concept more thoroughly and also present some recent papers that have focused on the deletion function of inhibition. But I would argue that, you know, paired associate learning, while we don't often think about this kind of task also requires deletion, in that in order to do well on this task, you really need to move your attention along the list and not linger on previous pairs while you're studying the current pair. So for instance, when I'm trying to learn butter and crystal, I should now put cabin and football out of mind. Otherwise, I might form associations across these pairs that I don't really want to form because they'll interfere with my memory performance at retrieval. And so we showed this actually, this was a study with Ali Trell, Lynn Hasher at U of T. We had participants encode a list of paired associates. They saw one pair on the screen at a time. And then we tested their memory for those pairs using an associative recognition task. So participants had to distinguish between intact pairs, so those are ones that they saw at study, versus rearranged pairs. And we had two kinds of rearranged pairs in this task. We had near rearranged pairs that were taken from successive trials, so N-1 trials at encoding. So for instance, they would see barrel and traffic, and contrasted these near rearranged pairs with far rearranged pairs such as dragon and eagle that in the first experiment happened 9 trials apart, and in the second experiment 7 trials apart. So if older adults have trouble putting recently attended information out of mind, so for instance, barrel and turkey, they might be more likely to bind those words to the now, the pair that's in the current focus of attention, like olive and traffic. So they might be more likely to false alarm to these near pairs at retrieval than they would to the far pairs. And this is precisely what we showed. So this is proportion of false alarms here on the y-axis. And this is from experiment 1. And we can see that for older adults, they're making many more false alarms to these near repairings than to the far ones. Whereas for young adults, it doesn't really make a difference how far apart they were in the study list. And we replicate that in another group of older adults trying a slower study rate. They're still making more false alarms to near than to far. And again, this was all between subjects. So in a second experiment, we replicated the effect using a within subjects design, with older adults, again, making more false alarms to the near rearranged than the far. So this suggests that older adults form these associations across successive pairs at study. And these cross-pair associations might actually contribute to older adults' typically higher rate of false alarms that we see on these associative memory tasks. And now the question is whether this sort of tendency to bind over time does it also extend to memory for more complex events, like those experienced in everyday life, or the closest approximation that we can offer in the lab, which is events that are taken from movie stimuli. So one way that we can study event perception and memory in the lab, and this has become quite popular, is to use naturalistic stimuli such as movies. So for instance, this is the film that I've used previously, or we used previously in the Cambridge Center for Aging and Neuroscience project that I was a part of. But this movie was also has been used by Yuri Hassan in some of his work. In the CAMCAN study, we measured participants' neural activity while they watched this movie, and compared it to that of young people. So I'll just play you a little clip from the movie here, so you can get a sense of what it's like.
Where'd you get it? Birthday? How many bullets you got? Well, box full. There. What a cheesy gun. Can I try yours? Nah, please. No, go on home. You're home for good, really? Well, it's a little tough to do business in a country that's small.
So as you can see, we would say that when we change scenes from the boys playing quite nastily outside to now this living room scene where the adults are making cocktails, that scene change sort of serves as an event boundary in the film. And unfortunately, while memory for the movie wasn't tested in the CAMCAM project that I mentioned, we recently ran a new study that used this exact same film to address two main questions. So first of all, is this question of whether older adults form associations across event boundaries during the film. And a question that's sort of secondary to the current talk, but was actually the primary focus of the study, was whether age affects eye movement synchrony during naturalistic viewing. That is, do older and younger adults look at the same things when they're viewing a movie? And we are interested in this question, just as an aside, because a lot of work has suggested that young people show a high degree of neural synchronization when they watch these complex stimuli, such as movies. So for instance, this is taken from Yuri Hassan's 2010 TICS paper with an fMRI time course from a particular region here, with the average shown by the black line, but all the individual subjects are shown in the colored lines. And you can see that there's a high degree of correlation across subjects when they watch the same film. And this is seen over wide swaths of the cortex. And this seems to be driven by the fact that people are paying attention to the same information at the same moments in time. So for instance, people also tend to show a high degree of eye movement synchrony when they watch the same movies. And this is more so for things that are very captivating, such as this Hollywood trailer here. So this heat map shows that everybody's sort of looking at the same thing when they watch this, versus a home movie, which might not be directed as well, so it might not be as captivating. And using the CAMCAN data, Linda Geerligs and I have shown that neural synchrony tends to decline with age. And this decline tends to be most pronounced in the frontal parietal control network. So this is a network responsible for top-down attentional control. The medial prefrontal cortex, which is critical for remembering the past and imagining the future, and also integrating incoming information with sort of schemas or your existing knowledge. And also in the medial temporal lobes, including the hippocampus, so regions that are critical for memory. This is where we see the most pronounced age-related declines. And we think that some of these declines are due to maybe age-related changes in attentional control, in that these measures that were taken outside the scanner, measures of fluid intelligence and reaction time variability, which are both related to top-down control, particularly synchronous. So we have our average synchronization score across several networks. This is from a different paper of ours. Higher synchrony, especially in older adults, related to better performance on the fluid intelligence test. It also related to less variable responding on a choice reaction time test, suggesting that less synchronous people are the ones who have less sort of top-down control. And that led us to this new question of whether age differences in attentional control also lead to reduced eye movement synchrony with age. So are older adults looking at different stuff as well? So in this new study, it was an eye tracking study. We tested 24 young and 24 older adults while they watched the same movie from the CAMCAN study. And this was followed up by two different memory tests. First, a cued recall test, and then a free recall test. And the cued recall is the most important in this case because we included two different types of clips that were the cues for the cued recall. First, we had these between event clips, and those were clips that were taken just before an event boundary. So for instance, here they are having drinks in the room, and then a scene change happened, and next they're in the bedroom, and participants were just supposed to say what happened next in the movie. And this was contrasted with these within event clips. So these are clips taken from the middle of an event, and participants, again, are just supposed to say what happened next in the movie. And our hypotheses about these, so first of all, given the work of Eziet and Devashi, who showed that young people have better cued recall when a cue is taken from within an event than just before an event boundary, we would expect people to have better cued recall for the within than the between clips. And given our work on hyperbinding and older adults' tendency to form these broad associations, we actually expected older adults to possibly do better for the between clips than the young adults. And indeed, this is what we found. So this is the percent correctly recalled on the cued recall tasks. First of all, we're seeing that main effect in both groups, in that both groups are recalling more correct events following the within clips than the between clips. But for the between event clips, our older adults are actually outperforming the young adults in this case. Although I should say that the event by age interaction was only a trend. So the interaction isn't quite significant here. And it's pretty remarkable, actually, that older adults are doing this well on this task. And we actually see that this is mirrored in the free recall data. So their free recall, we use the autobiographical interview to score those data, dividing people's details into these sort of more internal or episodic-like details. And we can see actually that there's no age difference in the number of internal details recalled from the film. But we are seeing the classic pattern of older adults recalling slightly more external or semantic-like extraneous details related to the film. And we also were able to come up with another category in this case, which we called misinformation. These were incorrect details recalled from the film, and older adults recalled more misinformation than young people. In regards to the eye movement synchrony, we actually saw no age difference in mean eye movement synchrony across the whole film. Or even when we looked, we used sort of sliding time window over time to see if there's any periods where one group was more synchronous than another. We only saw one short little significant period where actually older adults showed greater eye movement synchrony than younger adults. So this suggests that older adults' reduced neural synchrony that we see with is not caused by them looking at different things in the film. So we related eye movement synchrony to our measures of memory and actually didn't see any relationship to the number of internal or external details that participants recalled, but actually eye movement synchrony related to the misinformation. So the less synchronous people, the people who are looking at different stuff, recalled more incorrect information, and this effect wasn't moderated by age. So older adults seem to form these associations, these broad associations across event boundaries. And whether this is harmful or helpful to memory may really depend on the task that's being used. You could think of these cross-event bindings as being detrimental to, precise detailed memory or the precise temporal order of things, but it actually might help people in their free recall, and it could actually help older adults to make connections across the entire story narrative. Age differences in neural synchrony don't seem to be due to eye movement differences, and this might be because eye movement synchrony is really driven by bottom-up attentional capture. And eye movement synchrony related to memory errors, but not correct recall for the movie. So just some final takeaway conclusions, or what are the takeaway messages I want you to take from this talk. The binding process itself does seem to remain relatively intact with age. What changes most is attentional control, and it really depends on how we test associative memory. Failed suppression of previously attended information seems to lead to these broader associations over time. And this can have implications for event memory from everyday life, or as we show in the lab, memory from movies. And it really points to a new way to sort of improve event memory with age. If we could help participants to sort of change the event or provide a large sort of contextual shift, then this might help improve older adults' memory for everyday events. So I'd like to say thank you to everybody who was involved in this research, all of our funders, and thank you for your attention.